introduce myself. I'm Shiry, assistant professor at TTIC. And normally,
We can't hear you. There is no mic.
There is no mic. There is no mic.
It's on.
It's on? It's on? Can you hear me?
Now it's better. Yeah.
Is it better?
Yes.
Do
Better.
you need it higher?
There we go. Yeah.
Okay. Normally, I usually talk about social cognition, but today I'm going to move to the darker side of the workshop here, and I'm going to talk about the model of the world that AI systems might have in their head. And what I want to start with is to state something that might be obvious to you, which is unless we talk about robotic embodied systems, AI systems never actually see the real world. They only get to see these artifacts that we humans, we create and we feed into them. So you might use a picture from here and from here and from here and from here. And then what we do is we train AI methods on these snapshots of reality. And somehow, from these fragments, our AI needs to figure out or infer the world that produced these snapshots. So this is kind of like looking at the outputs of a bunch of art students and trying to reconstruct what the subject matter was. So imagine I showed you thousands of paintings of elephants, different viewpoints, different artists, different styles. And now I ask you, can you infer what an elephant looks like? Probably, okay? Could you infer things that were never explicitly painted? Maybe, right? And this is exactly the situation that our models are in. So this raises some interesting questions. One question is what would count as a good model of the world? And another question is how can I reach into someone's head, whether it's human or AI, and read out this mental model? So thank you, Lenore, for setting me up so nicely, because actually Kenneth Craik, we're going to go back to him because he proposes an answer to both of these questions. And we are going to read. I'll read it out to you. If an organism carries a small-scale model of external reality and of its own possible actions within its head, it should be able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize the knowledge of past events in dealing with the present and the future, and in every way to react in a much fuller, safer, and more competent manner to the emergencies which face it. All right? So let's squint for a minute, and I think I can convince you that what Craik is actually saying is that if you have a good mental model in your head, you should be able to reason about possibilities, forecast the future, and generalize beyond your experience. Now, what you might notice is that Craik is not defining a model of the world by its contents. He's actually defining it by what it allows the organism to do. So because mental models are latent, they're inaccessible, the evaluation can be behavioral. So in other words, we don't have to read out the models. We don't have to do what Jacob suggested this morning and ask the model to explain itself. We can simply probe the affordances that it provides. So Craik gives us this explorational picture, a small-scale model in your head. You can use it to reason about the world. But before we get carried away, it's worth remembering that human mental models are very, very far from perfect. And somebody that emphasizes this exactly is Norman, and he tells us that human mental models are incomplete. They're unstable, we forget them all the time. They're unscientific, so we have all kinds of superstitious beliefs about the world. They're parsimonious. We're very much willing to do a lot of legwork just to keep our models simple. It's very hard for us to run these models in our head, and they don't have clear boundaries. So different models often mix together. So I believe that our goal shouldn't be to ask whether AI systems possess perfect internal replicas of reality. The interesting question is maybe, do they possess useful internal models that support certain capabilities? All right, so Craik describes a small-scale model in the head. We can make this more precise. One useful abstraction that we might use for what a model of the world might look like is a representation of the current state and a model of how that state changes. So together, this allows us to simulate possible futures. So a model of the world is not just knowledge, it's a tool for simulation. Here's a simplest abstraction. Okay, we have a state, we have a dynamic or a rule for how this changes. And once you have this, you can roll the world forward. Here's a state comes in, next state goes out. You can take this next state, feed it back in, and get the state after that. This is what we call forecasting or predicting the future. And in this framework, it's just repeatedly applying the dynamics over and over again. But the nice thing is that this is not only about time, and here's a key idea, and it's kind of cute. Reasoning and forecasting are not different capabilities. There are two ways of using the same model. Forecasting, we're rolling forward in time. Reasoning, we change the input action and simulate different options or counterfactuals. So reasoning and forecasting are both simulation. Generalization is not a simulation. It's a property of the model itself. It tells us whether these capabilities extend beyond familiar situations that we've seen before. Now, in classical settings, we write down the dynamics, but in modern AI, we learn them from data, usually directly from data. But the structure is the same. It's a model that we can use to simulate. Okay? So a model of the world, something you can use to simulate, reasoning and forecasting, just two ways of running that simulation. So this gives us a concrete idea of how to test Craik's definition. We can't usually read out what the system knows, but we can ask, can the system use its internal model in order to simulate the world? And so we know that if a system has an internal model, it should be able to do reasoning, forecasting, and generalization. These are observable affordances, and what we could do is test them by probing the behavior of the system. In this talk, I'm going to discuss two different lines of work that try to probe at these capabilities in different AI systems. It's just two simple examples of how you might do this. So we're going to look at reasoning in the context of spatial understanding and vision language models. We're going to look at forecasting and generalization in the context of motion and behavior prediction or forecasting. Let's start with reasoning. Here we're going to talk about vision language models. Okay, these are pre-trained large models that should, first of all, they have visual and they have language grounding, and they're potentially capable of implicit simulation, or at least we hope so. And the question is whether these VLMs can reason about spatial structure that is only implicitly represented in their training data. And so this is work that I did with a bunch of very cool people at Google DeepMind while I was there. So here we're specifically interested in what you might call large-scale spatial representation. So we're talking about city scale, okay? This is not within a room, your grid cells in the box, okay? This is whole city. And the interesting thing here is that you only have partial visibility from any location. You can't see the whole space. And so in order to represent the spatial arrangement of the space, you have to rely on locomotion and path integration in order to get the full representation. So what we do is we use these very interesting videos that people post online for some reason, which are called walking tours. And these are real-world, high-resolution videos. They're very long. They might be an hour long. And these are usually a single-person, first-person view, and they're walking down a city, in this case Amsterdam, and just showing us what it looks like. And what we do is we take these walking tour videos and we show them to pre-trained VLMs, and then we ask them spatial understanding questions about the physical space in which the person walked, okay? And then around these videos, we design a whole benchmark. But the question, okay, well, how do you ask questions about spatial understanding? Okay, so thankfully we have the whole history of cognitive psychology who has studied this, and especially started with Tolman, the idea of mental maps. And from this literature, we know that there is basically 3 levels of spatial understanding. You can think about the level of landmarks, which basically means, can you identify and localize salient objects in space? Route knowledge is talking about how do you think about egocentric turn-by-turn representations that link two different locations. And in the survey or map knowledge level, you might think about world-centric maps top-down that integrate together multiple of these routes. Okay, so we design our questions to hit all three of these levels. Here are just some examples. We have many different tasks. Here are just a couple examples. So for example, in the landmark level, we might ask, here's an image of a location. Have you seen this location before? Has it appeared in the video? If yes, what's the distance to that location from where you are now, from the end of the video? In the route level, we might ask, have you been here before? Have you closed a loop? So here's an example of a path with a loop and a path without a loop. Of course, the models are not shown these maps. These are just for you to look at. They only see the videos, and they were expected to tell us something about the world just from the videos. Okay, so we have all of these tasks in these three levels, and we have the videos that we collected. The problem is that it's very difficult to get answers to these questions. So we have all these questions, but we only have videos. So what we do is we ground videos onto the map using automatic methods. There are methods today that can take an image and give you a pretty precise GPS of it. So we actually translate the videos to the map, and then we can use this translation to come up with minimal human annotation for ground truth. So from all of this, we take all these questions. We have multiple questions per category, about 1,000 overall in this benchmark. And for each question, these are not open-ended, even though these are language models. We want to be a little bit, more careful with what we ask. And therefore, we have 5 options per question. Okay, so this is literally testing reasoning about different possibilities. Michal.
Yeah, given that you grounded it to a map, it still doesn't mean that the camera saw a particular landmark, even though you passed by it.
Yes.
The question is, do you expect it to know that the landmark is there or to have seen the landmark?
Yes, so the way we treat the landmark questions is we actually do that from the pixel. So we take a view that has been there before in the, the tour, and then we ask, have you seen this place before? So
Yeah,
we're not relying on the map.
No, so how do you have ground? Do you check that this landmark was visually seen in the video?
Yes, we do that with computer vision.
Okay.
Yes, which you might, just matching.
But during training of the model, it might have seen a lot of images from Amsterdam already.
That's fine. I give it to you. All right, it's fine. You can have that.
Okay.
All right. So what happens in practice? Humans are green. Models are all the other colors. The answer is that they're not doing very well, except they actually excel at landmark recognition, which you should expect, right? Because they know how to do computer vision. And they outperform humans at loop closure detection. And this is one of the things that we thought, this is kind of curious. We didn't expect this to happen. So it's just one of the things that we kind of drilled into in this work. And so, what do we know about biology? We know that biological organisms use path integration, right, in order to solve some questions of have I been here before. So there is the recognition, but there is also a lot of path integration information, and you basically track your movement and your rotation to see where have you been. But VLMs completely fail at this physical tracking. And here are some examples. I'm not going to go into it in detail, but just so you see the idea of if you look at the traces, what happens in practice. So the model first identifies, okay, this is the end of the video. This is what I'm going to look at. I'm going to need to say what this is. It identifies the location. Here it's wrong, doesn't matter. But it continues frame by frame to say, oh, have I seen this? Is it here? Is it here? It's basically looking for an exact match, which is very good at doing because it does have a vision model in there. And there's basically no indication that any of these models do any form of path integration in order to solve this loop closure task. It's just doing visual search. Okay, so this is just one example of our findings. We have a lot more, but I just want to give you a taste.
How do you know what the machine is doing? I missed
It's looking, so it's doing what we really do really well in computer vision is instance recognition. If I say you have some image of something and then I ask, is it similar to that? Is it the same place? We can solve that very easily. That is what the model is doing.
VLM, that's what VLM is doing.
That's what it seems like it's doing. If you believe, Jacob, that you can look at the
Seems like,
explanation. Yeah?
how do you reason about what VLM is doing?
What we are doing, okay, first of all, we look at the, can it answer the question, but then we actually go into the thinking traces that we ask it to spit out, similar to what Jacob talked about
So
before.
that's what the machine tells you.
Yeah, it's what the machine tells us that it's, if we ask it to, it's not an explanation in hindsight, it's an explanation of walk us through what you're doing.
But we had a previous talk that says that machines don't know what they're doing.
I know, I understand. Yes, so that's all we got. Until Jacob tells us how to do this correctly, this is what we got. All right, but so much with language, which is not really my field. Let's go to vision, okay, and throw language behind normal language here. So until now, we looked at simulating different spatial arrangements and probing Craik's kind of try out different alternatives idea. But now we're going to look at simulating future states by forecasting. Okay, and the question is, can we train models to anticipate future states of the world or future sequences, like Robert said this morning? So this is a collaboration with Nirja, who is Jitendra's student, and I think is no longer here today, while she was at DeepMind with our friends there as an intern. So really, what we're asking here in motion forecasting is whether models can forecast behavior. Okay, and what I mean by behavior forecasting is the ability to observe someone else's actions, be able to predict what they're likely to do, so that off the top of that, you could decide what to do in response. Okay? This is obviously scientifically important if you're studying animal behavior. It's also challenging with animals because there are many different morphologies and there's a lot of non-rigid motion. The data is pretty hard data for us vision people. And then there is a question of what type of representations enable behavior prediction. And I went into this, I had a whole talk 2 years ago here exactly on this, so I will just be brief and tell you that in language, predictive models have been a huge success. And part of this success is because NLP is really easy, because they have discrete word tokens. So if you take a large language transformer, it might take as input a prefix of words as context, and then it auto-regressively predicts the next word in the sequence. Beautiful, discrete tokens that you can really compare to each other and you know what's going on. But in vision, we have no tokens. Like, what should a visual prediction token be? We can think of a whole spectrum of possible options that lie between low-level and high-level representations. On the left, we have pixels, which is the most raw type of visual information that we might use. And on the opposite side, we can think of using objects directly in the 3D world. But something you need to consider before you pick is that imposing more physical object-level priors is going to make your life much easier when you try to predict, because you're going to live in a much lower dimensional space. You're going to need much less data and much less compute to do this prediction. So why not predict in this cheaper 3D model state? Absolutely, if you have a 3D morphable model, you should do it. Okay, that is what you should do. And we have these beautiful models for humans. But for animals, we have some solutions, but they're very much handmade. Humans, we can scan in a 3D scanner. Animals, literally, they took Schleich animals, which are these little figurines, and scanned those. We only have very few of them, and they're not very interesting set of...
But there are also other, in this range, there are lots of other possible visual features. Why not use low-level or high-level features from pre-trained foundation model and so on?
The first part of your question is excellent because you're preempting what I'm going to say. And the second part of the action we'll take in the Q&A, okay? So, so why not work with pixels? Here's an example from Sora, from OpenAI. These are not exactly pixels, they're pixel patches, they're implicit, doesn't matter. Let's call them pixels, okay? And what you can see is that these little wolf cubs basically reproduce like nobody's business, because working with pixels or pixel patches doesn't impose any physical priors. And so we might think, oh, we can learn these priors from data, but if it was even possible in practice, it would be very, very expensive. So, as Michal, thank you for sitting in the front, says, why not use something in the middle? Okay, in this work, and I have other possibilities in other works, but in this work we decided to focus on something in the middle, which is 2D point tracks. And you might ask, okay, why is this a good idea? So here's an example. Consider these sets of 2D points. When they're static, 2D points look like random collections. But once they start moving, the human brain sees 3D motion in these tracks. So tracking 2D points and predicting in this space might be a good idea. And so thankfully now we also have the technology to track any 2D key point in video. And here's an example of a method to do this from DeepMind. There's no prediction of the future here, okay? This is just tracking points in video. If you do any sort of animal behavioral studies, you've already seen something like this, only you guys are a little bit in the dark ages, and you're only looking at a few key points at a time. And this is the state of the art of, animal motion tracking. There's no forecasting here. We're just tracking. This is recognition, key points on the video itself. There's no learned motion model. These still rely on sparse hand-annotated key points. And as friends here from neuroscience can tell you, you have to annotate and train these things per species and per environment. If you take your mouse, you move it to a different type of box, you have to do it all over again. So what we want to do in contrast, we want to do two things different. We want to forecast animal behavior, and we want to do this across a whole slew of species, in this case, of mammals. So here's the main idea. We take an RGB video, we extract these camera-stabilized, very dense point tracks, capturing the ground truth motion. And now the model is going to observe a little short history of motion, 4 frames. We're going to outline it in gray. And from this history, it's going to forecast future motion. Okay, everything beyond the gray box is generated by the model. So this is not pattern matching, okay? It's rolling a learned simulator forward. Not going to go into how exactly we train a simulator. We can talk about it later, but this is the idea. And so with such a model, if you train it on a lot of data, you can forecast motion across a wide range of species and behaviors. And here are just some examples. I think Allison says she has to show a cute baby. I'm from Vision. I have to show you beautiful pixels. So again, the goal of forecasting point tracks is, given a short motion history, I want to predict the future. And the main technical insight in this whole work is that we can treat these point trajectory as our token of behavior prediction. Okay, this is going to be our word when we think about behavior forecasting. Now you can ask, okay, well, how do we evaluate anything like forecasting quantitatively? Normally, you think, okay, I have some conditioning. In this case is the past. I'm going to have my ground truth future and my predicted future, and I can just compare them with an L2 loss and call it a day. The problem is that that assumes a deterministic future, but the real future is stochastic. I might have multiple possible futures that are all correct, and I want to take them into account. So how do we evaluate this? One way to do this is to just, the simplest type of modeling is to say, let's take a Gaussian, fit it to the ground truth distribution, take another Gaussian, fit it to the predicted distribution, and look at the distances between these two Gaussians. And one type of metric that does this distance very nicely is the Fréchet distance. And so I can show you numbers of how we do based, relative to baselines, but it's more interesting to just see what it looks like. So here is our prediction and a couple of baselines. Okay. Here's another one. Because we have this stochastic modeling, we also can sample multiple random seeds. So instead of just having one outcome, one future that we forecast, we can have multiple ones. All right? Yes?
The trajectories are predicted as an ensemble or as individual trajectories?
And they're as an...
As a collective?
It's a collective. Each one of them is a separate token, but they're predicted together for the whole.
What you could do is instead of predicting the future, which is more random, do like BERT, take the beginning and the end and try to predict the middle.
Absolutely.
And then you'd have less uncertainty.
Absolutely, you could do that too. Yes, that's just a different type of modeling, yes. Okay, so so far was about future prediction. I'm just going to show you, just for this same model, for the sake of time, that it can also generalize for different distributions. So we've looked, our training data was all mammals, but it nicely transfers to birds in this case, semi-transfer to insects, and even to robo-dogs. The interesting thing about this one is that it's not actually how robot dogs walk. Okay, they go one by one. But because of the morphology of these legs that are bent behind, my personal hypothesis is that it thinks it's kind of more like a hare, and so it's trying to do a jump that would work better with such weird legs that you might have. Okay, so far for Craik, I'm going to take just a moment for a little aside, okay? If you were here in 2024, you might know that some people here, like Philip, seem to think that models of the world learned by different systems are all going to eventually converge to a single Platonic representation. But we beg to differ, and in a recent work that's led by Sophia, who's there in the back, and you should direct all questions to her, with Alosha, what we show is that it might be that there isn't one Platonic model, and instead that every organism may have its own Umwelt or worldview that is dictated by the point of view that they have of the world. This is all I'm going to say about this. Sophia is right there. Okay, so to summarize, do AI systems have internal models of the world? Well, the answer depends on what you might mean by such a model. If we follow Craik and ask whether they can use internal models to reason, forecast, and generalize, the evidence is increasingly compelling, but, incomplete. What we kind of talked about is that reasoning and forecasting can both be viewed as simulation. Reasoning, we simulate alternative possibilities. Forecast, we simulate the future forward in time. And generalization determines whether these simulations remain useful beyond your familiar situations. So we're beginning to see some evidence of behavior that suggests that some internal model of some aspects of the world are starting to form. But the challenge is, of course, to make these more robust and general and reliable. We're definitely, in my opinion, not there yet. Thank you. Yes. Well, you asked already. Yes.
I also assume.
You also asked already. Somebody who didn't ask, I was told that it's very polite to let the trainees and students ask first. So, please, any student questions? Yes?
I think this is a nice question, but just want to see where these key points for motion tracking. Like we know the existing knowledge of what points are the key points to track, or
So that's one of the main differences between what we are doing and what people do now with Deep Lab Cut, if you know these systems that do tracking in animals. What we are doing is we're just sampling randomly on the surface of the animal as many points as we can compute. Okay, so we don't actually right now have an association between the point and some physical part of the body. It's something that we should add in order for it to be directly applicable for behavioral modeling in a neuroscience lab, for example, and it's something that we know how to do, we just haven't done it yet. Yeah. Yes?
I understand perfectly like why training good models to predict the movements of animals is useful. That's clear. I don't see why phrasing it in terms of like if there are internal models or not. What does this add to this kind of
Is it what? Is it
endeavor?
what?
Like you are phrasing all of this in the framework of having internal models or not, but in fact what you are doing, you're just training models to predict well how the animals will move. So I don't
Yes,
see
that's true. I mean-
what's the added value of this kind of reasoning that you are proposing?
Yes, so in this case, we're doing animals for various reasons. It's one niche. The same type of technology is being used, or similar types of technologies are being used in other settings. For example, in robotic settings, people don't actually do this, but you can imagine this in driving settings. In situations where you actually interact in a closed loop in the world, you can imagine how this type of forecasting of other agents' behavior is already starting to get integrated into the loop of what you might think a world model or model of the world might be useful for. Jack?
You're probably not going to like this. But,
Already I don't like it.
we all want there to be a world model in our heads because it just makes sense that that's what you would do. But, I argued on Monday that the evidence for a world model as opposed to just some sort of probabilistic Bayesian thing in humans is really poor. And your talk makes me feel like you guys in the neural network world are in the same boat.
I don't disagree. I don't think we know. I think part of, actually me personally, I'm trying to tell here is a very cautious story. I don't think that these models have world models. I think there is a hype, I guess we're recorded and streamed, but in my personal opinion, that is not where we are. It's a good way to get funding. It's a very good way to start a startup, but I don't think we're there at all.
Well, both those things are important too. So
Yeah, I know. So that's why maybe we shouldn't stream this. Yes?
Yeah, we actually have a paper archived where we do a tracking in different ways using actually the entire mask on an object level, and helps a lot, particularly for our data where we have super highly socially interacting animals. So I was wondering if, because all the videos I saw, they are only single animal predictions. So what happens if you have really 5 animals jumping around each other? What does
Very
this
good
point-
question. Yes. So we have a lot of my personal previous work has to do with interaction of different people, different agents, that sort of thing. This is kind of a very narrow intern project where we said, let's just get the technology working so that we can move on to add multiple animals together. You are completely right. We just have not done that yet. Yeah, okay. All right, I think this is a good time to stop. Let's take, now I switch my hats. Let's take maybe a 5-minute breather, wiggle around. Afterwards, we're going to come back and we're going to go back to our closed door discussions. If you're a member of the audience, thank you so much. We will see you tomorrow morning. All right? Perfect. Thank you.